Hello, I'm audible.
Yes, sir, you are audible.
Okay, thank you. So first of all, a very special good afternoon to all of you and a warm welcome to today's session, which is over the EV motor deep dive from fundamentals to the performance optimization. So first of all, I'm very thankful to all of you for giving a valuable time to this session. So in this section, we will be covering the topics and giving exposure towards the EV motor fundamentals, type of motors used in the electric vehicle, and their working principles, key performance at all parameters, optimization in the real world. So before I begin, I request everyone to kindly keep off the microphones and please keep you on mute. And there will be in last there will be Q&A sections, and if there's any question in between, you can drop on the chat box. Now, I'd like to introduce Mr. Akash, who will be the today's expert trainer from our end, who has a strong expertise in EV technologies, motor design, and performance optimization with hands-on industry experience. Without taking much time, I'd like to hand over to Mr. Akash. Over to you, Akash.
Thank you, Suresh. Good evening, everyone. How are you all? All good? I hope everyone is fine.
Yes, sir.
So please, if you have any queries, you can unmute yourself till you can mute yourself, okay? It will not create any disturbance in between. So today we are, can you please turn off your mic, Kriti? Hello. Please unmute yourself. Hi. I hope now it is clear. My screen is visible. So today we are going to learn something very important about the EV motors. As we know, electric vehicles are grown very fast in India and around the world. Without a motor, an EV cannot move. So today we will understand how EV motors work and why they are so important. Okay. So tell me one thing. What is the heart of a petrol car? It is our engine. Same in the case of EVs. Our heart is the EV motors. Okay. So first we'll discuss why do EV motors matter. Now let's understand. In a petrol vehicle, the engine is the heart, and in the electric vehicle, the motor is the heart. So the motor is the main primary propulsion source in our EVs, which converts the electrical energy we got from the battery to the mechanical, converts the electrical energy into the mechanical energy and transforms it into the wheels. Okay. And one more thing, it means it has a motor, like the rotation turns the wheels when we get the mechanical energy. And it has a very major one thing, it gives us high torque at 0 RPM. As we can see in the engine vehicles, the torque gradually increases with the speed when we increase the speed. But in the EV motors, we get the highest torque in the 0 RPM. So, as you have seen, whenever you sit on the EVs, it gives a jerk. like it gives an instant torque. That jerks gives us the instant torque means, okay. And it also eliminates gearbox complexity. Like you have seen engine have more complex design, but the motor is very simple. It has only a single speed gearbox, okay, that is fitted in the transmission system inside below the vehicle and connected to the wheels, okay. And instant torque delivery, it gives us instant torque delivery, and which improves our acceleration and drivability, okay. Now let's see the EV powertrain architecture. Just give me a moment. Now we will understand the complete EV powertrain architecture. This diagram shows how energy flows inside an electric vehicle. Power, basically you can see power starts from the battery part. Then this is the battery pack. You can see this is our battery pack, and it stores high voltage electric energy. This is the main energy source of our electric vehicle. All power comes from here. All the power comes from our battery pack. Then comes the battery management system. I think you have learned in the last session about the battery management system. So this is the battery management system. I think in the last session you have learned about the battery parts in depth. So we are not going to discuss much about the battery part. We will discuss about in today's session about the motor part. Okay. So then comes the battery management system. It monitors battery voltage, temperature, and safety. And it also protects the battery from the overcharging and overheating. Without BMS, our battery may get damaged. So this is also the control part in our battery management system. Then comes the inverter. Okay. This inverter converts the direct current into alternating current. Okay. Basically, the battery gives direct current supply to the motor controller, and that motor controller changes the direct current supply to the alternating current. It converts DC to AC. Okay. So, does anyone know about how it is getting changed? As you have seen, we charge our mobile with the DC supply, but from the socket we get the AC. That same things applies here. The inverter control the DC, but DC to AC. Then it transforms the power. It directly gives the power to the electrical motor. This is our electric motor. Okay. It converts electrical energy into mechanical energy, and it produces the rotation. When the rotation comes to the drivetrain, here is the gearbox and the differential part. I think you have seen differential in the heavy vehicles. I think you might have seen the differential part, how differential looks. Wait, I will draw for you. Like you have seen in the heavy vehicles, like you have seen in the trucks from the back, like this type of section, you can see from the back. We call it as the differential. Okay, here is the gearbox, basically gearbox or the mechanism inside this differential. Okay, but in EVs we have a very simple architecture. So we use only a single speed gearbox. Okay, we use only a single speed gearbox. Then comes to the drivetrain. This is our drivetrain. Then finally power reaches the wheel. Okay, and you can see here the green line. You can see here the green line. It is our regenerative braking system. Like it is a regenerative braking loop. It converts, basically its work is to convert mechanical energy back into electrical energy. Okay. Basically it converts mechanical energy back into electrical energy. I will discuss about this in depth in the next slides. Okay. Basically, I just want to give the full EV powertrain architecture here. Okay. And this is the vehicle control unit. This is our vehicle control unit. Basically, we call it as the brain of our electric vehicle. Okay. So its function is to give commands to the auxiliary systems in our EVs. It controls motor, inverter, battery. It takes signals from the sensors part. Basically, it decides how much power to send to the motor. Like we can whenever we accelerate or throttle, we give throttle to the vehicle. It decides how much power we have to give to the motor. Okay, this is our brain of our electric vehicle. Do remember this, okay? Brain of our electric vehicle. Then comes the DC-DC converter. It is also the main important thing. What is the function of, does anyone know what is the function of DC-DC converter? You can unmute yourself. Whoever want to give the answer, or you can type on the chat box also.
Sir, am I
Yes,
audible?
yes, you are.
8 step-ups or step-downs the voltage.
Absolutely correct. So yeah, so basically it whenever we get the power from the battery, it may be 300 volt, 300 volt, 400 volt, we get power from the battery. And DC-DC convert the high voltage to low voltage direct current. Okay. So this is our DC-DC converter. Like we have need of 12 volt in the lightning part, infotainment part. So DC-DC converter works there. And one more thing here is the charger. You can see here is the onboard charger. Like in the onboard charger, basically we get AC supplies. Okay, it is slow charger, but in the public station charge, we get the direct supply. As you can see, we get the direct supply, so our battery get charged fastly in the public station charger. But in the onboard charger, the charging process is a little bit slow from the as compared to the public station chargers. Okay. Now let's see the motor construction part. To understand how a motor works, first we must understand its part. Okay. You can see here is the stator. You can see it is our stator, and this one is the rotor part. Basically, stator is the static part in the motor which do not rotate, and rotor is the rotating part. Okay, stator is the static part and rotor is the rotating part. And then comes the shaft inside the motor, which is fixed with the rotor and the bearings for the. Now see what comes inside the stator. There is a laminated core. You can see the laminated core, because you might have seen in the motors the linings like this inside the motors. You might have seen. These are the laminated core. Okay. These are very small in the, like you can see 0.1 to 0.3 mm it has thickness. Okay, these laminated core windings have only 0.1 to 0.3 mm have thickness. Okay, and here you can also see here is the 3-phase windings. 3-phase winding I will discuss in the next slides. Okay, in the depth. You can see in the static part we have 3-phase winding, laminated core, and it is the stationary part. That's it. Okay, and we have windings like this. It is made up of aluminum. In some motors you can see some are aluminum. They use aluminum windings, and some are copper. Basically in the EVs we mostly use copper windings. Okay, And then comes the rotor part. Rotor is the, in rotor, we have permanent magnets. You can see north, south. These are the permanent magnets we have fixed in the rotating part. Okay. Here, you can see north, south poles. When stator magnetic field interacts with rotor magnets, okay, that rotation happens. Yeah, like you can see the magnetic, whenever we see magnets, it always try to attract with the magnetic field. Okay, that's why we have placed the magnets inside the rotor, and it helps us in the torque production also. Okay, whenever okay, this is our rotor part. Then comes the shaft, which is fitted with the rotor. Okay, and in between the stator and rotor part, there is a difference of 5 to 1 mm. There is a, we called it as the air gap. Okay, we called it as the air gap between the rotor and the stator part. It is very small, you can see, but for increasing the magnetic field, for increasing the torque, we have to maintain this gap. Okay, if it is too close, it might get stuck inside and might get heat. Okay, the air gap is critical for performance. Then comes the shaft. It is connected with the gearbox, and it gives delivery to the main wheels. Okay, then bearings. Then you can see the bearings. Basically, bearings for the smooth rotation and to reduce the frictions in the motors, we use the bearings. Okay, and this part we called it as housing. The outer part we called it as the housing of the motor. Okay, so might you have understand the it is very simple. Not it don't has more complex design. We have stator in the motor. Stator is the static part, and then comes the rotor. Rotor is the rotating part, and the magnets are fitted inside the rotor. Okay, and then comes the shaft and the bearings, and the outer part is the housing part. Okay. Now let's see the some design parameters of the motors. Okay. These are the important factors engineers consider while designing an EV motor. Basically, motor's performance depends on these parameters. You can see here the number of poles. These number of poles define the motor has magnetic poles. You can see this is our rotor, and it has magnetic poles north, south, north, south. These are the number of poles. Okay, basically in the motors we have 8 to 12 poles in the rotor part. Okay, in the motors we have basically 8 to 12 poles inside the rotor. But higher poles may reduce maximum speed. Okay. Then comes the number of slots. Number of slots, basically they are the spaces in the stator. Basically, they are the spaces in the stator where copper windings are placed. More slots means more smoother operation. It basically it improves magnetic distribution. Okay. These are the number of slots. Then comes the air gap. I told you before, 0.5 to 1 mm we have to maintain this air gap between the rotor and the stator part. Okay, smaller air gap, basically smaller air gap improves efficiency of the motor. Okay, then you can see here the stack length. Basically, stack length is nothing, just if this is the length of motor core. You can see that it is the length of motor core. More magnetic area means more torque. Okay. Longer stack length increases the magnetic effect and gives the more power. Okay. And this is also the shaft diameter D1. You can see this is the shaft diameter. It is about 5 to 8 mm. Basically, this data is for the smaller motors we use in the drones. Okay, that's why its diameter is 5 to 8 mm. In the heavy vehicles, in the 4 vehicles, there might be have 13 to 15 mm of diameter of shaft. Okay, we use basically these motors in the drones. Okay, and there are some more parameters, like you can see that the electromagnetic parameters are also there, mechanical parameters are also there. Okay, and some thermal parameters are also depends of the motor designing. Okay, then now let's see the basic working principle. This is the basic working principle of a three-phase motor. Okay, you can see phase A, phase B, phase C, what it defines. Okay, basically the stator, this is our stator part. Basically the stator receives three-phase AC supply. Okay, from the you have seen that from the battery we get the power, and from the battery to there is an inverter. You have seen inverter. That inverter converts the direct current supply to three-phase AC supply. Okay, that inverter part converts the direct current to three-phase AC supply. Then that power supply is given to the stator part of the motor. Okay, and these three phases are placed at a 120 degree, around 120 degree in the stator. Okay, 120 degree. Do remember all these three phases are placed around 120 degree in the stator part of the motor. Okay. Then comes the rotating magnetic field. As you can see, when we give supply to the static part, there is a copper windings you have seen. These copper windings create a rotating magnetic field. You can see the rotating magnetic fields looks like this. Okay, these are the rotating magnetic field, and there is a laminated core also in the stator part. Okay. Then comes the rotor. You have seen in the rotor we have in the rotor we have magnets inside the rotator part, and these rotors try to these magnets try to align with the magnetic field. Okay, these magnets try to align with the magnetic field which is generated inside the copper windings. Okay, a rotor always chases the magnetic field which is generated inside the windings of the motor. Okay, so you have seen that this is the diagram. You can see the magnetic flux here. Okay, then you can see. Now let's discuss about the power speed graph. Okay, power versus speed graph. By this you will easily get understanding about the power and the speed we get from the motors. Okay, first understand, here is our x-axis, this is our x-axis, and this is the y-axis. Okay, first understand the blue line. Here blue line shows the constant torque region. It is the torque region. Okay, does anyone know about what is torque? You can unmute yourself. Why do we need high torque in the EVs? Can anybody tell me?
For initial pull.
Sorry.
For initial pull.
Yeah,
The
yeah.
starting speed.
Yes, yes. Torque is the pulling. Basically, torque is our pulling power. So we need torque to rotate the wheel. Okay. So here you can see. Here is the blue line is our shows the constant torque region. Then green line is showing the constant power region. Okay. This is our green line. This shows the constant power region. Then comes the field weakening region. Okay. Now you can see here. Here from the 0 to 4000 RPM, torque is constant. We are getting a 250 Newton meter of torque, which is our constant. In this region, motor gives us the maximum pulling power. Okay. In this motor gives us the maximum pulling power, and here you can see the base speed. Base speed. Basically, what is base speed is when the motor reaches the rated power. Basically, base speed is what when the motor reaches its rated power. Here you can see the rated power is around 120 kilowatt. Okay. Below base speed, the torque become constant. Below base speed, the torque is constant. And after crossing the base speed, we can see the instant decrease of torque here. As you can see, we can see here the instant decrease of torque. Okay. Now, constant power region, you can see from 4000 RPM to 6000 RPM. Power is constant. You can see here the power is constant, 120 kilowatt. As speed increases, our torque gets decreased, but power remains same. Okay. Power, as you can see, power is equal to torque into speed. Okay. Then comes our field weakening region. Basically, it is above the 6500 RPM. We get our field weakening region. This allows motor to reach higher RPM. Okay. Basically, field weakening region is what? It allows motor to reach higher RPM. Okay. To increase speed, magnetic field is reduced. Okay. As you know, when we increase the speed, magnetic field is getting reduced. Okay. Basically, field weakening region, in this region, whenever we don't give acceleration or motor, at this time our motor starts generating power. Okay, basically from this here field weakening region, our motor start working as a generator because it giving back voltage supply to the windings of the motor. Okay. And here you can some key equations also. Power is equal to tau into omega. Basically, you can see here power is equal to tau into omega, and omega is equal to 2 pi n upon 60. Now this tau is the power and the speed tau is the power we are getting, and omega is the angular speed. Okay. Suppose we are getting a torque of 200 Newton meter. Here we are getting got a speed of 250 Newton meter. But let's suppose we are getting a torque of 200 Newton meter. Okay, at 5000 RPM. You have to bring pen and paper for the calculation. Okay, we are doing some calculations in this also. Okay, so bring pen and paper with yourself, or you can take the screenshots of the slides also. Okay, But for the calculation, you must need a calculator or a pen and paper. Okay. Then P is the power. P is the power here. And what is what is 2 pi? From where we get the 2 pi? Okay. Does anyone know what is 2 pi? Does anyone know what is 2 pi? From where we get the 2 pi? Basically, it is the diameter of the motor, total diameter. As you can see, 2 pi. Pi is the radius, and for a full diameter, we get the 2 pi. And n is the speed. N is the speed. And 60 is the time. 60 is the time. Minutes to, basically it is minutes to second. Okay. Now I have told you like we are getting a 200 Newton meter of torque. Okay. Now to calculate this, how will you calculate? We have a formula of 2 pi n upon 60, and the power is getting calculated by tau into omega. So first we will calculate it like 2 equal to, I will erase some part, wait. Now see. Now you can see 2 pi into n is the speed. We are getting a 5000 Newton meter of speed. And at 200 Newton meter of torque. Okay. Divide by 60. I hope you are also calculating this. Okay. So 2 pi, what is the value of pi? 3.14. Okay. Into 5000 into 200 upon 60. Please calculate, anyone, and give me the answer. I am waiting. Please calculate. 2 into 3.14 is 6.28 into 5000. Does anyone have calculated? You can unmute or please give me the answer. You can calculate the power of a motor by using these calculations. Okay. So in the future, whenever you try to choose a motor for your for anything you have prepared in the projects, so by this you can calculate all these things.
1466.66.
1466.66. So basically we are okay. These are we can approximately take it as a 150. Okay, so we are getting a 150 kilowatt of power at 5000 RPM and 200 Newton meter of torque. Okay, so we are getting a 150 kilowatt of power from at 200 Newton meter. That torque changes with the speed. Okay, but in EVs we are getting from the 0 RPM to the base speed, we are getting a same Newton meter of torque, because the current gets directly because the current remains constant in the motors, but as you have seen in the engine, the torque gradually increases. Okay, this is the main reason we are getting in 0 RPM at full torque. Okay, 200 Newton meter of torque. And you might have seen that whenever you travel through the electric vehicle buses or electric vehicle two-wheelers, we get a instant jerk. That jerk is the instant torque we are getting from the motors. Now you have understand it? Okay. So by this you can calculate the power of a motor. I hope everyone have understood it. By now to calculate the torque, how can we calculate the torque? Here is the formula. Torque is equal to force into radius. Basically, torque is equal to force into radius. Okay. Suppose we are getting 1000 we are getting 1000 Newton meter of one force, and the radius, this radius is of the motor part, like you have seen in the shaft. Okay, radius is in the motors we have a radius of around 0.3. So basically the torque we get at this point is around 300 Newton meter. Okay, basically we will get the torque here is about 300 Newton meter. Okay, now let's discuss about the back EMF and RPM. Okay, when motor rotates, it generally gives voltage. It generates voltage inside it. That voltage is called back EMF. EMF means electromotive force. Okay, back electromotive force. This is our, whenever motor rotates, it generates voltage inside it. As you have seen, here is the field weakening region. Here is motor. Here at this part, motor is generating the power inside it. Okay, back EMF means back electromotive force. It always try to oppose the applied voltage. Okay, it always try to oppose the applied voltage. At that times motor behaves like a generator, and when it is rotating. Okay, here is one more equation here you can see, and back EMF is directly proportional to the revolution per minute. Okay, here is one more equation. Is the back electromotive force, which we counts in the voltage. Okay, then comes the KE. It is our motor constant voltage. Okay, we are doing some calculation in the starting, but later on we will discuss all the types and in the depth about it. Okay, but first in the starting we are just doing some calculation, just because you will know you will get more understanding about how you will choose the motor. Okay, then it is the motor voltage constant, then omega is the angular speed, and you have learned this formula. Omega is equal to 2 pi n upon 60. Okay, then you can see here the graph. Back EMF is increasing linearly with speed. Here you can see back EMF is increasing linearly with speed, and at 0 RPM we are getting zero electromotive force. With the increase of speed we are getting more EMF. Okay, so we'll do here one more calculation to calculate the back electromotive force. Okay, now we will just suppose we are getting back EMF and the motor voltage constant, which is our KE. Okay, that KE we can take it as a 0.5 volt, because we are not getting much power from the EMF. Okay, so it is 0.5 we are supposing, just okay, we are just taking it as a number. It might be different in the different motors. Into the angular speed we can take it as, okay, let's suppose take a speed of 3000 RPM. Okay, first we will convert the RPM to angular speed. Okay, first we will calculate the RPM to angular speed. How we will calculate? 2 pi into 3000 upon 60. You can give me the answers, okay? Or you can also do the calculation in your notebooks also. How much angular speed we are getting here? Can anyone calculate for me? 2 pi into 3000 upon 60.
So 314.
Yeah, we are getting 314. It's radian per second. Okay. 314. Now calculate the EMF. Now calculate the EMF for me. We are getting a EMF of 0.5 here into 314. How much it is?
157.
Yes. We are getting 157 volt back EMF. Okay. I hope you are understanding all. I hope everyone understand. Everyone is getting. Okay. Can anyone? Yes. Okay. If you have any queries, you can unmute yourself. Okay, or ask me. Okay. We are. I want you to be more interactive. Okay. Now let's see the types of motors. Basically, which types of motors we are using in the EVs right now, and in the future we will which types of motor we will use. And okay, so these are the types of motors we are using in the EVs. Today in the market, you have seen these types of motor. Okay, first one is the BLDC motor, and second one is our PMSM motor. Third one is our induction motor. Fourth one is SRM. Okay, and fifth one is our SYNRM. Can anyone tell me about the full names of these motors? What is the full form of BLDC motor?
Brushless DC motor.
Correct. And what about PMSM?
Permanent magnet synchronous motor.
Excellent. And you might have seen induction motor. And what about SRM?
Slip ring motor.
Slip ring motor, it is little bit incorrect. It is our switched reluctance motor. It is our switched reluctance. Okay, switched reluctance motor. And SYNRM, can anyone tell me the name of this motor?
Synchronous reluctance motor.
Yeah, absolutely correct. This is our synchronous reluctance motor. Okay. You can take the screenshot of this and you can write it on the papers as well. Okay. Do remember all these motors. I will discuss in depth about all these motors in the next slides. Okay. Then I will ask you about the full forms and okay. We have basically 5 types of motors here: BLDC motor, permanent magnet synchronous motor, induction motor, switched reluctance motor, and synchronous reluctance motor. Okay, here we have given the types of motors. In BLDC motors, magnets, yes. PSM motor also has magnets, and these 2 motors don't have magnets. Okay. And if you compare the efficiency of all these motor, in the PMSM motor, we are getting a high efficiency. You can see here, in the permanent magnet synchronous motor, we are getting a very high efficiency. Okay, and in the switch reluctance motor, the efficiency is medium, and synchronous reluctance motor also has high frequency. And depending on the cost, it depends on the size of the motor we are buying. Okay, it depends on the size of the motor. Because if you take a BLDC motor, small BLDC motor for the drone, it might cost lower. Okay, But BLDC is mostly using in two-wheeler and three-wheeler. Okay, basically we are using BLDC motors only in the two-wheelers and the three-wheelers. Okay, the best motor we are using nowadays in the four-wheelers, that is our permanent magnet synchronous motor. Okay, and the induction motor, it is getting used in the premium EVs. Like you can see the Tesla Model S. These cars have induction motors, and they are also using the permanent magnet synchronous motor. You can take an example of Tesla models. Okay. And switched reluctance motor is mostly getting used in the heavy electric vehicles. Okay, and the synchronous reluctance motor is the modern platform here. Like it is not that much in the use, but some companies are using this motor as well. Okay, does anyone have query till now? You can ask me. Do remember the name of these motors, okay? Do remember the name of these motors. But I haven't discussed about this in the previous slide. This is our brushed direct current motor. This motor was like you can see the widely used motors till now. You have seen this motor. Like in the toys, we are using this motor. This is our brushed direct current motors. In the fans, we are using this brushed direct current motor. Okay. So now see the construction here. We have bearings here in this motor. Okay. But in this motor, in the previous slides, you have seen the magnets was inside the rotor. Okay. But in this brushed direct current motor, we have fixed stator magnet here. In the stator part, like means the fixed part, static part, we have magnets here. And in the armature, here is the windings. Here is the windings. Okay. And one more thing, it is our commutator part. Basically, here it is our commutator part. And these are the brushes. That's why its name is brushed direct current motor. We have brushes here. Okay. You can see here. Okay. Now, how it is getting worked, can anyone tell me? You might have used these motors in the toys. Can somebody explain me about this? If anyone know? Okay. Basically, these brushes supply current to the rotating armature. Okay. Basically, in this, the brushes supply current to the rotating armature, and that commutator changes current direction. Okay. In this, the commutator changes the current direction. Basically, you can see here the brushes we are using, but we are not using these motors in the EVs. I am just I am discussing just about to know. You must know about these motors as well. Okay. So here are some advantages as well. It has very low cost, and it has a very simple control. Due to its size, it has high starting torque. It is rushed and reliable, and there is no complex electronics like the other motors we are using in the EVs. Okay, and it has some disadvantages. That's why we are not using in nowadays in any motors in every model. As you can see, drones are as you can see in the future, we may use some other motors as well, but we have declined this motor just because it has high maintenance and limited lifespan, and due to the brushes, it reduces the efficiency of a motor. and heat is also getting generated due to the friction cause inside the rotating part, which is our windings. Okay, and it also creates some noise. Okay, and in the environmental contaminations zones, like you can take an example of for in the gases factory, you can't use this type of motors even in the fans. Okay, because it may generates a spark in due to the heat. Okay, that's why this motor is not you can see nowadays you can't see this type of motors in the factories as well, because there is gases maybe. So we are also using BLDC in the fans as well nowadays, you can see. Okay, and it has a very lower power density as compared to other motors. This is our brushed direct current motor. Okay, anyone have doubt? If anyone have doubt, you can ask me. Okay. Now here you can also see the we can calculate the speed or efficiency of this brushed direct current motor by calculating this. Okay, here n is the speed. Okay, here n is the speed and E is the back EMF. Okay, E is the back EMFs. 60 is the seconds to minute, and A is the number of parallel paths. Number of parallel paths means the slots you have seen in the motor back. Okay, these are the number of parallel path, and P is the number of poles. Basically, number of poles is what? The number of magnets we are using in the motor. You have seen we are typically I have discussed before, we have basically 8 to 12 poles inside the motors. Okay, for a simple calculation we will not take that much poles. So P is the number of poles, and this is our phi. Phi is the flux. Okay, how much flux means magnetic flux in each pole. Okay, then can anyone tell me what is Z? Basically, Z is the total number of conductors in the armature. Okay, total number of conductors. Total number of conductors in the armature. Okay. Now let's take an example. Okay. Suppose E is 220 volt back. That is our back EMF. Okay, you have to calculate it for me. Okay, is the suppose back EMF we can take it as 220 volt, and we will take 4 poles. Okay, for a simple calculation, and phi is the phi we can take it as 0.02 Weber. Okay, we are just taking a simple calculation, and Z is the total number of conductors in the armature. So total number of conductors we can take it as the 200, and A is our what? Number of parallel paths. Okay, we can take it as number of parallel paths 2. Can anybody calculate? Can anybody calculate it for me? 220 into 60 into 2 upon 4 into 0.02 into 600. Please calculate and give me the answer.
550.
550. Very fast. Nice. So we are getting a 550 RPM, revolution per minute. Okay, we are getting a 550 revolution per minute in this motor. Okay, does anybody have any doubt or queries? You can tell. Okay. Then let's move forward. Then comes the mostly used motor in our two-wheelers and the three-wheelers. Okay, which is our BLDC. BLDC, what? Brushless direct current motor. Okay, which is our brushless direct current motor. Now you can see here is our stator. Okay, we have seen before. We are getting a three-phase supply in the stator part. It generates rotating magnetic field, and it has laminated core. Okay, and the rotor. This is our rotor part, which has magnets and typically have 4 to 8 poles, and it produces torque. Okay, then comes the magnetic flux here. This is the magnetic flux. Okay, how it works, basically how it works, BLDC motor. Okay, we are getting a direct current supply. We are getting a direct current supply from the battery, and inverter converts it into the three-phase alternating current. Okay, basically in this motor we are getting a three-phase AC supply, and these three phases are 120 degree apart. Okay, and the stator part, it produces the rotating magnetic field inside the copper windings. Okay, you can see the magnetic field, how magnetic fields looks like. Okay, that it generates a rotating magnetic field inside the stator. Okay, and the rotor magnets try to align with the rotating magnetic field. Got it? When the magnets try to align with the RMF, so it generates the torque. Basically, it generates the torque whenever the magnets try to align with the RMF. It generates a torque. Okay. Then how these three-phase work? It basically works on the switching. Okay. Here there is the continuous switching and continuous rotation. That's why if switches won't occur, our motor won't move. Okay. If the switching won't occur, the motor won't move, because we have we are also use the motor controller unit. Okay. Motor control unit, I will discuss in the next slides about that part in the depth, which is our MCU, motor control unit. Okay, this is our brain. This is the brain of motor. Okay, so that motor control unit helps us in the switching of the phases inside the BLDC motor. Okay. And here is one more equation you can calculate. How can you calculate the speed of the motor? Basically, 120 degree is the phase angle. 120 degree is the phase angle, and F is the frequency. Basically, we get about 50 hertz of frequency in our normal household, and we can take 4 poles. Can anyone calculate 120 degree into 50 upon 4? How much it is? Can anyone calculate?
500.
Yes. So we are getting 1500 RPM. Okay. In this, it depends on the poles, because like I have chosen here 4 poles. You can choose 6 poles, 8 poles, 12, up to 12 poles you can choose here. Okay. You will increase the poles, or RPM may get reduced. Yeah. Okay. And here is one more equation here. T is our torque. K is the motor constant. Okay. K is the motor constant. This is the flux, and I is the current. I is the current we are getting. Okay. So let's do one more calculation here. How will you calculate the torque here? Okay. For example, let's take like we have calculated before as well. I think We have few more calculation in the next slides as well. So I hope everyone know how to calculate the torque. Okay. Now let's see the BLDC. Basically, what is this? BLDC phase firing. You know, BLDC motor does not use brushes. It defines because the name defines itself. The BLDC is the brushless direct current motor. Basically, it uses electronic commutation. Okay. In the brush direct current motor, you have seen the mechanical commutation. When the brushes touches with the commutator, it generates the it generates the electronic magnetic field inside the rotor part. But in the BLDC motor, we don't use brushes. So in this motor, we are using electronic commutation. Okay, that I talked about the MCU part, and in the MCU we have Hall sensor. Okay, basically what is Hall sensor? Can anyone know? Do anyone know about the Hall sensor? Does anyone know about the Hall sensor? You can unmute. Okay, no issues. Okay. First, we will discuss what is phase firing. What is phase firing? Yes. Okay. In phase firing, basically in BLDC, we energize 2 phases at a time. Okay. We have total 3 phases. In BLDC motor, we energize 2 phases at a time. You can see here phase A, phase B, and one phase will be off. Okay. One phase is positive, another phase is negative, and one phase will be off. Okay. This is called 120-degree conduction mode, basically. Okay. Basically, we have 6 steps here. Positive, negative, off. Then positive, the phase B will be off. Then the phase C is the negative part. Right? So total we have 6 steps. We can do see in the 6 steps to rotate the rotor part. Okay. Each, as you can see here, each step 1 show 0 to 60 degree. Okay. Then second step is 60 to 120 degree. Then 20 to 180. So each step is about 60 degree here. Okay. And the conduction mode is about 120 degree. Okay. So basically in each conduction mode, we are doing 2 steps. Okay. So we are doing 2 steps in each conduction mode. In the step, current flows from phase A to phase B. Same, phase C gets off, then phase A get energized. Okay, this phase firing flows like this. Like one phase will on, the rotor part try to rotate with the phases. Here you can see. Here you can see the one pole will get energized. So rotor tries to align with this pole. Then the next pole will get energized. So rotor tries to move forward. Then the next pole will energize. The rotor tries to move forward. Okay. By this you can see the rotor always start moving with the help of phases on and off. Okay. Like each phase conducts with 120 degree, you have seen. At any time 2 phases are on. Okay. And what is the role of Hall sensor here? What is the role of Hall sensor here? Basically, Hall sensor works on the Hall effect. Okay. So Hall sensor basically Hall sensor do what? It detects the rotor position. Okay. It detects the rotor position. Then they tell controller which phase to energize. Okay. You have learned about the vehicle control unit in the powertrain architecture. Then there is an inverter there that do the DC to 3-phase AC supply. Okay, this Hall sensor tells the controller which phase to energize, and that time the rotor tries to move forward. Okay, when phase A gets on, the rotor magnet will try to move forward. Okay, then next phase will energize. So that switching happens. Switching is continuously happening. Okay, and the Hall sensor tells the controller to which phase to energize. Okay. So just simply learned, Hall sensor gives the Hall sensor communicate between the controller, and controller gives direction to the phases. Okay. In the BLDC motor. Okay. So I hope you everyone have understand about this BLDC phase firing, how these are phases getting energized after each step. At 120-degree commutation, we have 0 to we have total two steps. About one phase 0 to 60 degree, then 60 to 120 degree. Okay, these are the electrical rotation. Okay, and these generates the torque ripple inside the motor. Okay. Now let's discuss about this more important motor, which is our permanent magnet synchronous motor. Okay, this is our permanent magnet synchronous motor. Okay, in this permanent magnet synchronous, we have basically it has two types. One is interior and another one is surface. Okay, another one is surface permanent magnet synchronous motor. Basically, mainly the difference between the interior and the surface permanent magnet synchronous motor is just the rotor part. Okay, if the rotating part is from the outside, then it is the surface permanent magnet synchronous motor. And if the rotating part is inside the motor, so it will be called as interior permanent magnet synchronous. Okay. First, now, can anybody tell me why it is named as permanent magnet? Can anybody tell me? You can unmute. Why it is named as permanent magnet? We have magnets also in the BLDC, but why we have used its used permanent magnet name here and the synchronous? Why it is named as permanent magnet synchronous motor? We also have magnets in the BLDC, but we have used permanent magnet name here. Anyone? You can speak. Nobody? All right, no issues. So basically, permanent magnets, because in this, the rotating part, we have this is our interior permanent magnet motor. Actually, the outer part here is not rotating, so the picture displayed the interior permanent magnet. Okay, the rotating part is inside here. Basically the magnets are embedded. Basically, the magnets are embedded inside the rotating part. That's why it is named as permanent magnet. Okay. The motor has only two parts, stator and rotor, but the magnets are permanently embedded inside the rotor part. That's why it is named as permanent magnet. And can anyone tell me about the synchronous? What does this mean? Synchronous. Anyone? Anyone?
Same speed as
Same speed.
rotating magnetic field.
Yes. Synchronous means same speed. It means the rotating part it means the rotating part is rotating at a same speed with the rotating magnetic field which is generated inside the copper windings in the stator part. Okay, that's why we have named it as permanent magnet synchronous motor. The magnets are fixed inside this, and they are moving at a same speed of the rotating magnetic field. Okay, and that's why we are getting more higher torque in this motor, and we are using this motor in the four-wheelers. Okay, that's why PMSM motor is widely using in the four-wheeler EVs. Okay, so same in this case, we are getting three-phase AC supply, and the rotating magnetic field we are generated, and the laminated core is there inside the stator part, and the rotator and the rotor has embedded NdFeB magnets. Can anyone tell me the name of this magnet? What is the full form of NdFeB magnets? Anyone?
Neodymium.
Yes. Neodymium. Again. Neodymium, iron, boron. Okay. Neodymium, iron, boron magnet. Okay. This type of magnet we have used here. Neodymium, iron, boron magnet. Okay. And it has a high torque, as I discussed before, because the rotor is rotating at the same speed and try to align with the motor. Okay. Same working principle here also. And the AC supply we are getting, and the rotating magnetic field is generated. The rotator rotates synchronously with the RMF. Okay. Then torque is getting produced by magnetic interaction plus reluctance torque. Just give me a minute. I will drink some water. Just give me a minute. Okay. All right. So I was talking about the torque production. Okay. In this, torque is produced due to magnetic interaction between the rotor and the stator part. Okay. Now here you can see saliency. Saliency. What is this? Can anybody tell me what is this? Saliency. Anyone? What does this mean? Okay, no issues. Basically, saliency is the internal permanent magnet. Okay, it is the interior permanent magnet synchronous motor. D axis. Basically, we have two axes, D axis and Q axis. Okay, D axis and Q axis in the motor. Okay, and if there is zero saliency, if here we have there is a difference between saliency, means that difference create additional reluctance torque. If the saliency is not if the saliency has a difference, if the saliency doesn't have difference, it is equal. It means there is no movement. Okay, if there is a difference, so the rotor tries to move forward. If there is no difference, then the rotor will not move. Okay, so that difference is must inside this PMSM motor. Okay, then anyone have doubt in this permanent magnet synchronous motor? You can see the structure here. This is the stator part. Okay, this is the stator and some plates, rotor hub here, steel plates, magnets inside this. This is our core part. Here is the rotor section. Okay. Anyone have doubt in this? Okay, all right. Now we will study about the induction motor. Okay. Basically, this motor doesn't use permanent magnets. Okay. In the BLDC, we are using permanent magnets. In the PMSM motor, we are using permanent magnets. But in the induction motor, we are not using permanent magnets. It works on the electromagnetic induction principle. Okay. And how it is working on the electromagnetic induction principle? I think you have known about this motor, induction motor. Anyone? They called it also as asynchronous motor. Yes, anyone was trying to ask something? Okay, all right. Basically, in this rotor current induced, the rotor current induced due to slip between rotating magnets. What does it mean? Okay. Like all motors you have seen, there is a stator and rotor. And stator receives the three-phase AC supply. Rotor is usually squirrel or case type. But in this rotor doesn't have permanent magnets. And how it is working? It is working same as rotating magnetic field is generated inside the stator part. Okay. The current is induced in the rotor. The current is induced in the rotor. That's why we called it as induction motor. Okay. We are inducing the current inside the rotor. That's why it is called as induction motor. Okay. And same the switching process we have discussed back. The switching process works like the Hall sensor detects the position of the rotor, and that gives the signals to the controller part, and controllers decides which phase to on and which phase to off. Okay. Same 120-degree conduction mode. In each conduction mode, we have two switching steps, and for a 360-degree smooth rotation, we have total six switching steps per cycle. Okay. Phase A on, phase A, phase B off, phase C on. This process repeatedly, continuously work. Okay. And there are some advantages of this motor as well. Like there is no permanent magnets, so the cost will be low. Okay, no rare earth magnets we are using inside the rotor. So the cost is, as compared to the permanent magnet synchronous motor, this motor costs lesser than the PMS. Okay, and it is rust and reliable as well because it has iron core inside. Okay, and it is good for high-speed rotor operations as well. We can take an example like in the Tesla Model S, like in the heavy-duty vehicles, we are using induction motor basically. In the Tesla Model S, we have used in the rear wheels. In the rear wheels, we have used permanent magnet synchronous motor, and in the front wheels, we have used induction motor. They have used two motors in the wheels. In the front, they have used induction motor in the Tesla Model S. Okay. And in the rear wheel, they have used permanent magnet synchronous motor. Okay. So this is the working of induction motor. In this you can see the diagram of this and how it looks from the outside. Okay, this is here is the motor shaft. Stator windings are same as before you have seen in the motors. It is in the stator part. Okay, and here is the end bracket, and here is one cooling fan. What is the use of this fan? Can anybody tell me why we are using this fan? Yes, you can speak up.
For cooling and protection of winding from short circuit.
Yes, because the heat is getting generated inside the motor part, and we are that's why we have used fan here for the cooling purpose. Okay, and as you can see the shape of this motor, and you have seen the shape of the engine as well. Okay, that is these motors shaped like this because we call it as the fins. Okay, we call it as fins. They reduces the heat generate inside the motor and release it into the environment. Basically, these fins designed to release the heat is generated inside the motor. And you have seen engine design also. It looks like from the outside like this. They are the fins. Okay, they are basically used to remove the heat for the heat removal. Okay. This is our induction motor. How many motors we have discussed till now? Brushed direct current motor, brushless direct current motor, permanent magnet synchronous motor, and this one is induction motor. Okay. Can anyone tell me the difference till now? I have discussed about the motors, difference between the PMSM, BLDC, and the induction motor. Major difference you have seen in these motors.
सर उन सब में परमानेंट मैग्नेट होता है, इन सब में इंडक्शन मोटर खुद का रोटेटिंग मैग्नेटिक फील्ड जनरेट करता है.
किन में?
सर अब तक जितने भी मोटर हमने देखे हैं BLDC, PMSM और BMDC, सर इन सब में परमानेंट मैग्नेट होता है, जबकि जो इंडक्शन मोटर है उसके अंदर वो खुद से एक्साइट करके रोटेटिंग मैग्नेटिक फील्ड प्रोड्यूस करता है.
Excellent, both sides. So in this, the rotor generates the electromagnetic field. The electromagnetic field inside the stator part is generated, and the rotor is made up of iron here. So it is getting energized and start moving forward with the RN. Okay, and same here the switching also, how it is getting switched with the help of Hall sensor. We are use Hall sensor. Okay, and that Hall sensor gives signal, communicate with the controller part, and controller gives the direction to the phases, which phase to on and phase to off. Okay, then let's let's now discuss about the switched reluctance motor. Okay, this motor is very different from the permanent magnet synchronous motor and the induction motor. Okay, it does not use permanent magnets. You can see the images here, how this motor looks like. Okay, we don't have magnets here. It is totally made up of irons. Okay. Let's see the basic architecture here. This is the rotating part, our rotor part, and this is the setter part. Here you can see the copper windings. Okay, that is getting generate that generates the RMF. Okay, Basically in SRM, only stator has winding. Rotor is just, you can see here the piece of iron here. Okay. Now let's see the working of this switched reluctance motor. Okay. When the current flows in the stator phase in this motor, the magnetic field is getting created. Okay. Then the rotor moves to position of minimum reluctance. Mark, listen to my words carefully. Then the rotor, when the magnetic field is created inside the stator, rotor moves to position of minimum reluctance. Minimum reluctance means this switching process. That's why it is named as switched. You can see the rotor is not getting aligned, is not aligned with the stator part. Suppose we can take this as phase A, phase B, phase C. Okay, phase A, phase B, phase C. Basically, it is 120 degree apart. Phase A, phase B, 120 degree apart. But when phase A gets energized, the rotor tries to move forward and try to align with this phase A. And you have seen in 120 degree rotation, we have two steps of around 60 degree. Okay, then the rotor tries to move forward and try to align with the phase A. But at that time, the Hall sensor detects the position of the rotor. That time, the Hall sensor detects the position of the rotor and tells the vehicle control unit to energize next phase. Okay, to energize the next phase, then phase A will get off. Then phase A will get off, and phase B will be on. Okay, then the rotor moves forward to the phase B, forward toward the phase B. And this process is continuously working, phase A getting on, phase B getting off. This process is continuously working and it generates the higher torque. That's why it is generating, it generates the higher torque inside the motor. Okay, this is the switching process. It is getting switched. Here he is doing switching from phase A to phase B to phase C to the minimum reluctance. Okay. Do remember one thing. Just rotor always try to align with the energized pole. Okay. Rotor always try to energize with the stator pole. Then here are some advantages as well of this motor. It has high temperature capability. Okay, it is cheap because it has no rare earth magnets, rust construction. Disadvantages, we have some disadvantages as well because it has maximum torque ripple. Can anyone explain me what is maximum torque ripple? What is torque ripple? Anybody?
Change in torque, variation in torque magnitude.
Yes, the variation comes in between the rotor. Like if the rotor is not rotating smoothly, okay, maybe there was a fault comes inside the Hall sensor. It is not working. It is not giving signals to the controller part. So that creates the torque ripple. Okay. And in this we have used iron parts, so there was a chances of maximum noise here. And due to heavy weight, it has vibrations as well, and it has some like complex control required. as compared to if we compare with the permanent magnet synchronous motor and the brush BLDC motor. Okay, so this is our switched reluctance motor. Okay, got it? Everyone got it? This about the switched reluctance part, switched reluctance motor. I hope everyone getting. Okay. Next, let's move forward to the next motor. Next motor is our synchronous reluctance motor. Okay. Synchronous, as you have told me before, it is the synchronous means the same speed. Okay. It is not in the market that much in the market today, but I thought you must know about this motor as well. Okay. So basically, this motor also doesn't use permanent magnets and does not have rotor windings. Okay. Basically, it uses ferromagnet iron rotor. You can see the different types of rotors, different types of rotors we have in this motor. Okay. These rotors are basically designed to generate the torque inside the motor. Okay. Produces torque due to differences magnetic reluctance. It produces torque because how it is generating torque. Can anyone tell me? Because it don't have magnet or in the does not have rotor windings. It also has the same concept. Rotor tries to align in direction of minimum reluctance, as I discussed in the switched reluctance motor. In this motor also, rotor rotates synchronously with the magnetic field. Okay, and here you can see the torque production, how it is producing. I talked about the saliency before. If LD is not equal to LQ, so that time torque is produced. Okay, if there is no difference, no reluctance torque will be produced. Okay, so that difference is must to generate more torque. Okay, we are basically these type of motors in the heavy vehicles we are using, like in the trucks or buses. Okay, this is the switched reluctance motor, and synchronous reluctance motor is basically used in the heavy vehicles. Okay. There is nothing more about this motor. Okay, I hope you have understand about this motor. There is simple working, same as before I discussed about the switched reluctance motor and the permanent magnet and the induction motor. Okay. If we compare this with the permanent magnet synchronous motor, torque due to magnets, torque is generated due to magnets plus reluctance, and in the synchronous reluctance motor, torque generates only due to the reluctance. Okay. Now let's discuss about some efficiency of electric motors. How can we increase the efficiency of a motor? And as we can see, every motors have different types of efficiency. You can see here the brushless DC motor typically have 85 to 95% of efficiency. These efficiency totally get distributed to the vehicle. Okay, but in the engine, in the fuel vehicles, we are only getting 30 to 35% of efficiency, because it is generating more heats. But in this, we have a very simple design, not a complex if we compare with the engines. Okay, so that's why it is providing more efficiency. BLDC provides us about 85 to 95% of efficiency. That's why we are using this in the two-wheelers and three-wheelers. And permanent magnet synchronous motor has a typical efficiency of 90 to 97%. And it has a high power density and excellent efficiency. Means there is less power energy loss in the environment if we compare with the BLDC motor. Okay, it has in BLDC motor we have moderate torque ripple, commonly two-wheeler, and this is in the modern passenger EVs. Now the induction motor provides us the efficiency of around 85 to 94% of efficiency, and in this we don't have permanent magnets. It is slightly lower peak efficiency. Using some performance EVs, we are using this induction motor. Okay. Then comes our switched reluctance motor and synchronous reluctance motor. They are similarly same. So they are providing 85 to 93% because they are used in the heavy vehicles, and it also produces torque ripple switched reluctance motor. And it has higher acoustic noise. Okay, and it is emerging in the AV applications. Okay, these are the efficiencies we have seen in, we are getting in the different types of motors. Okay, does anyone want to say anything till now? Any doubt, any query? You can speak anything if you have any doubt inside your mind. Okay.
सर वो जो आपने CNC के बारे में बताया था ना, उसको सर एक
Yes.
बार दोबारा से समझा दीजिए ना।
हाँ, मैं बताता हूँ। Basically देखो, basically saliency is the difference. Wait, basically saliency is nothing, just a difference, because suppose we are here is our 0 degree and it is the 90 degree, because if you see this rotor, okay, this is our we can take it as 0 degree and this is 90 degree. Okay, when there is a difference between the phase, okay, 0 degree and the suppose here is the phase A, okay, and here is the phase B. This pen is not working clearly. Wait. Yes. Suppose here we have the magnets. Here we have the magnets inside, and magnets in the rotor part, and rotor always try to align with the rotating magnetic field which is generated inside the coils. Okay. If there is no saliency means there is a difference. If there is no difference, so no torque will be generated. Means if the rotor gets aligned with the rotating magnetic field here, okay, then how will it move forward? How will it move forward? So it needs some difference. It needs some difference to rotate. Okay, to generate the torque, it needs some difference. That's why I told you that saliency needs we need a difference in the, we need some difference to generate the torque in the motor. Okay, so that's why I told you that this is the saliency. If there is no difference, no torque will be generated. Okay. Okay, so I hope you got this. This is the I hope you got this.
Yes.
Okay.
Yes, sir. Yes, sir.
Then comes the types of losses we see in the motors. Okay, we have seen here the efficiency to increase the efficiency, we see some losses also. Okay. And first one, some energy is always lost in the form of heat. Okay. So these losses reduced motor efficiency basically. So we have copper loss. Copper loss is the major loss in the motors. It is around 40 to 55% of loss we are getting from the copper. Okay. And this is the core loss. Okay, sorry. This is the core loss. Okay. Copper loss happens in the stator winding. Copper loss happens always in the stator winding. It is due to the resistance of a copper. Okay. And if we increase the current, so the copper loss will be increased. Okay. With the same, if we increase the current, so copper loss will also get increased. Okay. Basically, copper loss is dominated at high speeds. Okay. Okay. Increase करेंगे current, so current भी बढ़ेगा, dominated at high load. Then comes second one is our core loss. A core loss happens in iron core. Iron core means the laminated core winding I told you about in the later. Like this we have in the motor. We have laminated core like this. Okay. It has two parts: hysteresis loss and the eddy current loss. Hysteresis loss. Can anyone tell me what is hysteresis loss? Anyone? I want you to speak up. Please speak.
Losses due to magnetizing and demagnetizing in iron core.
Yes, absolutely correct. Basically, hysteresis loss is due to continuous magnetization and demagnetization. This hysteresis loss happen. Okay, and the eddy current loss is due to the circulating current in the iron part. Okay, eddy current loss is due to the circulating currents in the iron part. That eddy current loss happens. Then comes the third one, which is our magnet eddy loss. This is this caused harmonic flux. Okay, means magnetic field distortion creates small currents in magnet. Okay, basically field distortion creates small currents in the magnet. If you see, whenever we supply the higher current to the motor, due to the higher RPM, there may be a chance of magnets to loss. Okay. Then comes our fourth one is mechanical loss. Mechanical loss is just due to the friction. Okay, friction, and that friction happens in the bearing. Okay, that friction happens in the bearing, and then the air drag. Okay, these losses increases. Basically, these losses increases with speed. Okay, then the fifth one is our stray loss. Okay, these basically stray loss is nothing but just some additional losses which is due to the harmonics and the slot effects. Okay, it is not easy to calculate exactly, but we calculate just these are some just additional losses. Okay, and that's why I put it here. Okay, so 5 types of losses we have discussed. Copper loss, which is maximum 40 to 50% of loss we getting from the copper. Then it is around 20 to 30% loss we get from the core, and mechanical loss also we get 5 to 10% of bearing. Bearing basically is for smooth rotation, but there are some losses. Okay. Then let's see the thermal losses and the temperature effect. Okay. Let's see the thermal losses and temperature effect in the motors. Okay. You can see here the copper is equal to 3 times IR square into R. Okay. You can see here thermal losses. We can calculate all the losses by the formula. Okay. So here is 3 times means we have 3 phases. 3 phases. And in each phase, the current, we are increasing the current, and R is the resistance. This is our copper loss. Okay. More current means more heat. Windings, basically windings heat up because of resistance. Okay. Mostly EV motors use insulation class of class F, because class F can handle up to 155 degrees Celsius. Okay, because it can handle up to 155 degrees Celsius. That's why some more EV motors use class F. Okay, then comes the class S. It is used in the high performance EV motors. It can handle up to 180 degrees Celsius. Okay, but over 140 degrees Celsius demagnetization happens. Okay, and how this happens? Because when that much heat is generated inside the motor, the magnets will getting demagnetized. Okay, due to the heating. Okay, better to reduce this, or one more thing, you can see the lifespan halves for every 10 degree rise above insulation limit. Means for every 10 degree rise, the life of the motor will get reduced. Okay. This is like motor lifespan is it depends on the how you are driving the vehicle. And if you are doing the rough driving, like you're moving the vehicle at high speed, so more heat will be generated. So that time there may be a chance of getting magnets demagnetized, and the lifespan of the motors will get reduced. Okay. This is the basic concept, and there is one formula. You can write it down to calculate the speed. We can calculate the speed by like P total power. If we are calculating the power, so we are using P total. There is P copper plus P core. Like you can calculate how much loss we have get from the copper, then the core part, then the mechanical part, then the magnetic part. Okay, then the stray part. Like in the previous slide, you have seen all these losses. Okay, you can calculate all the losses, and you will get the power, how much power is lost due to the heating effect. Okay, but to for the better cooling for the EVs, to reduce the heat of a motor, we use for some liquid coolings and air coolings as well. Okay, like now you can see which cooling techniques we used for the thermal management in the motors. Okay, first one is air cooling. That is our you can see I have discussed in the fins. These are like the fins. Okay, these are like the fins. So they release the heat with the help of fins to the surroundings in air cooling engine. In air cooled motors. And in the liquid cooling, we used basically glycol. Okay, there is a liquid called glycol. We used to remove it to remove the heat of the motor. And here one more comes the oil cooling. Okay, here one more comes is our oil cooling. And how this oil cooling works? Basically, this motor is, if you take an example, this motor is used in Porsche Taycan. Porsche Taycan has used oil-cooled motor. That is our EV. Okay, and if you see the Hyundai, Hyundai Ioniq, it has also used oil cooling to remove the heat of the motor. Okay, and Tesla Model S also has oil cooling motor. Okay, then there is a advanced cooling. Then there is a advanced cooling which enhance the thermal stability, maintains magnetic safety below 140 degrees Celsius, so your motor's life will not get degraded. Okay, here is a integrated cooling and heat exchanger which is fitted with the motor part. Okay, that's same applies in the engines as well. We use liquid cooled engine, air cooled engine. Okay, same concept applies in the EV motors as well. Then this part is our MCU. Okay, we have discussed all the things which comes inside the motor. Now we will discuss the control unit part of a motor. Okay. What is motor control unit basically? Anyone have doubt till now? You can ask me. If anyone have doubt, you can just unmute that time or just you can speak up. Okay. Anyone have doubts? No, should I forward? Should I move forward?
Yes, sir.
All right. So now we will understand the most important, which is our MCU. Okay. As I told you before, this is the brain of our electric vehicle. Just look at it, how it is looked from the outside. There is a design difference depends on the vehicle. Okay, which type of MCU motor control unit, and depending on the size and shape of a motor, it also depends. Okay, basically it converts DC battery into 3-phase. Okay, and controls the motor torque and speed and manages regenerative braking. Okay, in the next slide you will see how regenerative braking works and how it is increasing the efficiency of a motor. Okay, and it protects the motor and the power controller, and how it is working, protecting the motor and the power controller, I will discuss. Okay, the brain and the power driver is of our electric vehicle. Okay, and this one you can see here the major hardware components which is fitted inside the motor control unit. Okay, look, you here in the power stage we have power module, IGBT SiC MOSFET. Okay, and DC link capacitor and liquid cooling plate. This is in the power stage, and in the controller stage we have gate driver board, phase and DC link current sensors, resolver, encoder. Okay, DC bus voltage. Okay, now let's discuss about first the power module part. Okay, this is the main switching. You can see here, these are the MOSFETs. Okay, basically MOSFET is for the switching, like I have told, from like a Hall sensor gives the direction to the controller part, and here is the Hall sensor, they are doing the switching. Okay, it converts direct current into high frequency alternating current, and these devices switches means switching thousands times per second. Okay, like how much if a motor is moving at 5,000 RPM. Okay, So that switch, you can take an idea how fast that switching getting occurs. Okay, so that is getting controlled and monitored by this MOSFETs. Okay, this is the main part. This is our and SiC means silicon carbide. It is made up of silicon carbide. Okay, and this is our DC link capacitor. Basically, DC link capacitor stabilize the DC voltage. Okay, and it reduces voltage ripple as well, and they store store energy for quickly switching. Okay, like capacitor we use for a small as a small energy device. Okay, so this is our DC link capacitor. Then comes the liquid cooling plate. It removes heat from the power module. Okay, power device generate heats power devices generates high heat. So liquid cooling plate used to cool that part. Okay, in the controller we used some chemicals like to reduce the heat. We use heat fins. Use heat fins to reduce the heat. Liquid, that is our liquid cooling plate. It reduces the heat which is getting generated inside this MCU component. Okay, then comes the controller stage. Controller stage, there you can see here it is written as DSP microcontroller. Okay, basically it performs real time calculations. Okay, DSP microcontroller what do real time calculations. Basically it runs on control algorithms. You can see like PWM and FOC. And what is PWM? PWM is pulse width modulation. Pulse width modulation. Okay. And FOC means field oriented control. Field oriented. My pen is not working. Field oriented control. Okay. So this DSP microcontroller runs on, basically it decides how much current and torque to produce. Okay, it is giving how much power you have to supply to the motor. Okay, that's why it decides how much current and torque will be produced. And then comes the gate driver board. Basically it sends switching signals to IGBT and the SiC MOSFET. Okay, basically it gives signals to the SiC MOSFET power module. Okay, gate driver. Then comes the current sensors, phase and DC link current sensor. These sensor measures motor current. Okay, basically motor control unit uses this data to control the torque. Okay, without the current measurement, we don't have proper control over the motor. Okay, that's why we use DC link current sensors there. Okay, then next comes the resolver, which is our encoder. Okay, basically it gives rotor position information. Okay, because motor controller need rotor position to control. Basically, motor control unit needs rotor position to control more accurately. Okay, that's why resolver and encoder links with the field oriented control, and it requires rotor position. Okay, then last one is our DC bus voltage sensor. Basically, DC bus voltage sensors measure battery voltage, and it protects system by over voltage. Okay, DC bus voltage sensor works for the measurement of battery voltage and to protect the system from the over voltage. Okay, these are the major hardware components. Does anyone have doubt till now in this? Anyone have doubt in this? Anyone? Okay. Let's move forward. Here you can see the EV inverter system and the architecture and the motor control. Okay, here is the architecture and the motor control part. Okay, here is the architecture. You can see it's not working. Why not? Yeah. Here you can see the power flow architecture. Here is the battery pack. Then the DC link capacitor comes. Then DC link capacitor to three-phase inverter. Okay, which is made up of there may be of MOSFET, IGBT. Okay, IGBT is same, just work like the MOSFET. Okay, it is insulated gate bipolar transistor. Okay, insulated gate bipolar transistor. And MOSFET is same, works like the in some inverters has MOSFET. Okay. Then comes the UVW three-phase. Basically, three-phase we mentioned we can we named it as UVW, three phases. Okay. Then comes the PMSM BLDC motor. This is the flow architecture. You can see how it is getting MCU, how MCU is giving a flow to the motor, power flow to the motor. Okay. Then second one is our inverter internal structure. Okay. And second one is our inverter internal structure. Here you can see 6 switching bridges. And how they are working. Basically, we also called it as 3 legs. You can see these are looking like legs, 1, 2, 3. These are the 3 legs. Okay, 3-leg inverter. Each legs control one phase. Okay, each legs control one phase, and switching devices turns on and off rapidly. Okay, these switching devices ons and off rapidly due to the switching. Okay, using PWM, we use pulse width modulation. Basically we see in the waveforms. Okay, these are the waves we are getting from the motor. So we see these waves with the help of one device, which is our oscilloscope. Okay. Yes. Then this is the inverter internal structure. These 3 legs do the switching. And then last comes the motor control unit. Okay, motor control unit, how it is work. Basically, here you can see the step by step. We have a speed command here. Speed commands to the to the controller. Then controller to PWM. Okay, PWM pulse width modulation to inverter. Okay, and then there is a microcontroller, DSP, gate driver, circuit, voltage sensor, resolver. Okay, basically microcontrollers direct power को switch नहीं कर सकता है. Okay, सिग्नल बेसिकली ये सिग्नल को एम्पलीफाई करता है. ओके, इसमें जो हमारा जो आइसोलेशन प्रोसेस रहता है ये क्लोज लूप में रहता है. लाइक इट इज इन द क्लोज्ड लूप फील्ड ओरिएंटेड कंट्रोल. यू कैन सी हियर. ओके, और दिस इज द main function to do the switching of MOSFET. Okay, then comes the voltage sensors. Some voltage sensors are also used in the microcontroller. Basically it helps to measure the DC bus voltage measures, and it gives the feedback control Okay. Then the resolver we have discussed. It provides the motor position uh, because the field oriented control to know the angle accurately of a rotor. Okay. Then here is the direct control vector like phase response. It gives the fast. It gives us the fast response and overcurrent and thermal protection. Then last one is our overcurrent and thermal protection, because when we give speed at high RPM, there may be chances of heat generation inside the motor. So overcurrent, when we increase the current and the thermal protection, it also the microcontroller also helps to control that part. Okay. Anyone have doubt? No. Okay. And this is our SiC, silicon carbide MOSFET. Okay, you can see how it looks. Okay. And what it do lower switching losses. Okay, it helps in lower switching losses to increase the higher frequency capability. It has smaller cooling system, higher efficiency, and it has also reduced the inverter size because it is very small. Okay. So that's why MOSFET we are mostly using in the control unit. Okay. Then here is the sensor versus sensorless and field weakening. Okay. Anyone have doubt till now? Please tell me. Anyone have doubt till now? Please tell me. Okay, no issues. So let's understand about this how motor knows rotor position. Okay, like for proper control, MCU must know the motor position. So that's why we use sensors to detect the position. Okay, if the sensors are used, so there may be a chance of 0.1 accuracy. Okay. If we are not using sensors in the motor, there may be a chance of not getting the accurate position of the rotor in the motor. Okay, so sensorless we are not using. That's why we are using sensor, like I have told you, the Hall sensor we are using, Okay, so we get the more accurate position of the rotor. Okay, and I have discussed about the field weakening region. When the motor reaches at the high speed, that with the increase of speed, the torque gets decreased. Okay, increase of speed with the torque gets decreased, and this region generates the power. Basically, this region generates the power inside the motor, which we named it as regenerative braking system. Okay, just give me a minute. I will drink some water. Okay. Now this is our regenerative braking system. Okay, and how this regenerative braking helps us to increase the efficiency of a motor, vehicle. So in regenerative braking system, you can see here, the power the energy we are getting from the battery to inverter, then inverters to motor, and the motor it to directly goes power to the wheels. Okay, but in regenerative braking system, the motor works as a generator. Okay, because after field weakening region, the motor stops generating torque. Okay, it starts generating voltage inside the rotor and giving power to the stator part, to the windings. Okay, and that, yes, anyone want to say anything? Someone's mic is on. Anyone want to say anything? Okay, so that times the motor is starting working as a generator because the kinetic energy we are getting, because the kinetic energy is getting, the electrical energy we get from the, hello. Can you please turn off your mic if you are not, don't have any questions? Thank you. So, wheels, here wheels rotate the motor. Okay, so the motor acts like a generator, and when it generates the electricity inside the motor, okay, that electricity flows back to the inverter part, which is our controller unit, and that controllers gives supply back to the battery. So the energy we are getting from the wheels to generate the electricity back to the battery, so that times our efficiency gets easily increased. Okay, our efficiency gets easily increased because we are not using external charger here to recharge our battery. Okay, in this regenerative braking system, the energy is getting generated and getting back to the battery part. Okay, this is how regenerative braking system works. Okay, I hope everyone understand this, how this regenerative braking system works. Anyone have doubt in this regenerative braking system? This is the torque and curve speed maximum region. After this, there is a decline. Okay, when you increase the speed, there is a torque. There is a decline in the torque generation. Okay, so in the regenerative braking system, we are getting energy from the wheels to directly back to the motor. Sorry, in the battery. Okay, then that energy we can also used in the different auxiliaries that are connected in the vehicle. Okay, now comes the little bit complex part. I will not say that this is the more complex. You can easily understand this as well. Okay, here are some calculation, like there is a motor selection logic and the performance requirements, like how you are choosing a perfect motor for your for a vehicle. Okay, how you will choose a better performance, so you will get a better performance in the in your vehicle. Okay, first here is the step one. You have to define the vehicle requirements. Okay, you have to check the vehicle mass, target top speed, acceleration requirement, gradability, wheel radius, and the transmission ratio. Basically, motor is selected based on these vehicle performance targets. Okay, and the second step is to calculate the required tractive force. Okay, you have to calculate all these to get a perfect motor for your vehicle. Okay, so how you are calculating these? These are some formulas here. So you can calculate it by to calculate and choose a perfect motor for your vehicle. Here is the F total, or total force you have to calculate. Here is the acceleration force you have to calculate, and F roll is the rolling resistance. Okay, rolling resistance of a wheel. F is the rolling resistance of a wheel, and F arrow, the aerodynamic, here is, it is the aerodynamic force. Means when vehicle moves forward, a aerodynamic force like a push comes from the front, that is the aerodynamic force we are getting. And then comes the gradability. Gradability means there is a slopy area. Okay, if there is a slopy area and you have which power, how much power is required to pull the vehicle up. Okay, that is we calculate it by these formulas. Okay, for F for the acceleration we calculate it as m into a. Okay, then comes the motor torque. How can we calculate the torque motor? By the total torque we are getting in the wheel and the force we are getting in the gear ratio. Okay, then the last step is our power requirement. Okay, power requirement we can calculate it by the total force we have get into the velocity. The velocity we have get it in the motor. Okay, and here is the formula you have. We have discussed about this and we have do some calculation in this. Okay, and n is the motor speed. Here T is the torque. Okay, so we will take a example of one vehicle and we will do some calculation of that here. Okay. Okay, let's take an example. Let's take an example of Tata Nexon EV. Okay, let's take an example of Tata Nexon EV. Okay, we have to calculate all this. You can take the screenshot of it, or I will ask you about all these formulas. Okay, tell me one by one. Okay, you can take the screenshot or you can write it down. Okay. Now we are taking an example of Tata Nexon EV. First, we will see the vehicle mass. Okay, vehicle mass. The vehicle mass Nexon have around 1700 kg. Okay, then comes the top speed. We will take the top speed is 120 kilometer per hour. Okay, then next is the starting acceleration force we get. Okay, like we can 0 to 60 kilometer per hour कितने स्पीड में जा रहा है 4.5 seconds. Okay, suppose 0 to 60 kilometer is जा रहा है 4.5 seconds. Okay, then we have to check the gradability also. Gradability, let's take a 20% slopey area. Okay, there is only a 20% slope. Okay, then let's take the wheel's radius. Wheel radius is around if we take in the meter, in the meter, so we can write it as mm. को हम लिख लेंगे 0.30 meter. Then comes the gear ratio. Basically, the gear ratio in the motors we have around 9.1 to 10. Okay, so we are choosing 9.1 here. Okay, then the motor's peak power. If you Google it, the motor power we are getting in the Tata Nexon is around 120 kilowatt. Okay, but that is just a company rated, but in physically we can see that it is motor power. Basically we get around 95 kilowatt to 100 kilowatt. Okay, the power we get from the motor. Okay, now tell me the formula for to calculate the acceleration force. Please tell me. We will calculate one by one. Please tell me the formula for acceleration to calculate the acceleration force? Anyone is here? Anyone want to say anything?
M into A.
Yes. F in right. F equal to M into A. Okay. And here M is what? Here M is what? Am I audible?
Mass.
Please, and no. Here M is the mass of a vehicle. Okay. And A is the acceleration. Okay. Like if we take any, we have seen 60 kilometer per hour is equal to, if we divide it by the, if we want it in the meter per second, can anyone tell me if 4.5 seconds 0 to 60 kilometer, if we calculate it, how much we will get in the meter per second? It is around, I think it is around 16.7 meter per second if we take in the meter per second. Okay. If we take the example of 60 kilometer, in meter per second, we will get 16.7, and about 4.5 second we are getting. Okay, 0 to 60 kilometer.
3.7 meter per second square.
Yes, 3.7 meter per second. Nice. Now we will calculate the 1700 into 3.7 meter per second. How much we will get? (1700) into 3.7 meter per second. How much we will get?
6290.
Yes, 6290. Is it correct, everyone?
Yes, sir.
Okay. So we are getting a force of 6290 Newton. Okay. So we have calculated this acceleration force. Okay. Now comes the next formula is rolling resistance. Then next comes the rolling resistance of a wheel. Okay. Rolling resistance, basically, the rolling resistance we take of a wheel is around of 100 mm we will take in the meter. If take in the meter, we will take it as 0.01. Okay. If there is a rolling resistance of if a wheel is 300 mm, so we will take the resistance as 0.03. Okay. Now, what is the formula of this? F roll equal to
M into
F
G
rolling.
into CR.
Yes, M into G into CR. Okay. Mass is 1700 kg. G is the gravity. Gravity is around is 9.81 meter per second, and CR is the coefficient drag. Rolling resistance, which is our 0.03. Can anyone calculate? Please tell me. How much rolling resistance we are getting?
10.2.
Can you repeat?
10.2.
Is it correct, everyone? Anyone have calculated? Is it correct? 10.2? Okay. Then next comes the aerodynamic drag. Okay. Then next comes the aerodynamic drag. So can anyone tell me how to calculate the aerodynamic drag? What is the formula of this? 1/2 rho A CD into V square. Okay, here 1/2 is we can write it 5. Okay, this is the aerodynamic drag into this is our basically this is the air density. Here this row shows the air density. Okay, the air density we are getting, it is as, okay, let's assume we are getting air density of 1.2. So we are getting into let's take the A. A is our basically A is our the frontal area. Okay, the frontal area of a vehicle is the A part, and here I haven't mentioned above. So let's take let's assume 2.3 meter square is the frontal area of a vehicle, and CD. What is CD? It is the coefficient drag. Okay, we are getting a drag of 0.335. I am just assuming all these numbers. These are just slightly up and down if we take any real example of Tata Nexon. Okay. Then last one is the velocity. We have calculated here the velocity 16.7 meter per second. 16.7 meter square. Okay. 16. Can anyone calculate it? The aerodynamic drag? How much aerodynamic drag we are getting? Please, anyone? Anyone is calculating?
134.7.
134.7. Nice. This is the aerodynamic drag, 134 or Newton. Or we can take it for a simple calculation, we can take it as 135 Newton. Okay. So this much aerodynamic drag we are getting in the vehicle.
Sir,
Then comes the, yes.
so is it 16.7 raised to 2 or minus 2?
16.7 you are saying about the velocity?
Yes.
Yes, 16.7 raised to power square. It is the square of 16.67.
I think in the formula it's minus 2.
This formula is minus 2. Yes, it is the velocity because the velocity gets doubled here. Okay.
Okay.
Yes. So the output we get is 135 Newton in the aerodynamic drag. Then we have to calculate one more thing, which is I will rub some. Please write all these things somewhere. Okay, because here is less. Okay, or you can take the screenshot. I will write here. By this, you can do all the calculations as well to select the vehicle. Okay. To know how much power we are getting from the vehicle and how much efficiency, how can we increase the efficiency of a vehicle. Okay. Then the gradability slope we have taken. Gradability slope is 20%. Okay. Gradability slope. Okay, this is the slope. I have taken around for 20%, means there is a slightly slope area. So basically this 20% is what is the formula of this to calculate the gradability? Is mg sine theta. Okay, is mg sine theta. So mass is 1700 and gravity is 9.81. And if we see the 20%, we can write it as 0.2. Okay. 1700 into 9.81 into 0.2, we'll take it as. Okay. How much we are getting? The gradability slope?
Three thousand 335.
Excellent, excellent. 3,300.
35.
So we are getting a 3,335 Newton of gradability slope. Same you can calculate. Now we will calculate all these things. Okay. Now we have to calculate the total force. Total force. How can we calculate? In the starting, we get the acceleration is around 6290 plus. Then tell me the rolling resistance. Rolling resistance, we got, how much we got the rolling resistance? I think I have wrote somewhere. I think it was around 167, I think. Yeah. Then the aerodynamic drag we got is 135 Newton plus. Then the gradability slope 3335. Please calculate how much total force we are getting in the Tata Nexon EV. Please calculate. How much it is? 6,290 plus 167. So,
9927.
9927 Newton. This much force we are getting in the Tata Nexon EV. We have taken an example of Tata Nexon. The vehicle mass we have decided and the top speed we have decided here. So this is the calculation you can calculate by choosing the motor. Okay, and this is the like this by this calculation you can check the performance of a electric vehicle, how much force it can bear, the aerodynamic force, the rolling resistance force, the gradability, okay, the aerodynamic drag. Okay, all these things you can calculate and choose the right motor and the best vehicle for you. Like if you know about the motors in the EV, it has PMSM motor and it has better efficiency because PMSM motor provides 90 to 97% of efficiency. So you will consider the PMSM motor firstly. Okay. So these are I have taken some real example, and this is the performance optimization. What is the loss reduction strategy you will choose? Iron loss. There are some iron loss, torque ripple minimization. You can optimize all these things by choosing the by considering all the things to perform to optimize the motor performance. Okay, iron loss, core loss. Okay, then this is the future of our EV. Okay, future of our EV motors. This is our axial flux motor. Okay, basically, but axial motors, you can see here the design. It is like a pancake design. Okay, this motor might use in the future. Okay, this is our axial flux motor. This looks like a it has a very compact and pancake type design, and it has a very high power and torque density. That's why we called it as a axial flux, and it can deliver more torque in the less volume. Okay, then come inside this, there comes the hairpin winding. It improves the copper fill factor, enhance cooling and efficiency. Then the integrated is axle. Integrated e-axle, basically it is all in one motor gearbox. It is a power electronics. Inside this there is a power electronics, lightweight and space saving. And as I told you, SiC inverter, SiC MOSFET, there is a MOSFET also, SiC, silicon carbide inverter here in this axial. It is lightweight and space saving. Okay, this is the future of our EV motors. That is our axial flux motors. Okay. So this is it. If you have any queries or doubt, you can ask me. Please, if you have any query, any point you have thought of, that part got out of your mind, please tell me if you have any queries. And the things you have learned today about the motor part, and we did some calculations to calculate the performance, to increase the performance or check the perfect motor for our vehicle. Okay. And I hope you have learned so many things today. I hope you enjoyed it. If you have any queries or doubt, please tell me. Anyone?
Hello, sir.
Yes,
Am
yes.
I audible, sir?
Yes, you are.
Sir, actually, means what guideline is requested over here regarding the, we can say, research work.
Okay.
Can you guide for the open source platforms? Means based on the, we can say, problem identification on EVs, like whether we have to go for PMSM motor or any other kind of special purpose motor. Because what is happening in the India, there is a, we can say, different temperature ranges are there. So we
Yes,
cannot
yes.
go with the same motors for various, we can say, states or various cities, sir. So how we can go for particular design, or what kind of modifications are required through problem statements?
Basically, if you are looking for the weather changes areas in our in the different areas in our country, okay. But as I have discussed about the PMSM motor, because it provides the higher efficiency, because that's why we are taking PMSM motors mostly in the four-wheelers, because we need higher efficiency and higher torque. It depends. It usually depends on the design of the vehicle. Okay, where the motor part is exactly fitted, because some vehicles use two motors, and some vehicles use two motors in the rear wheel and one motor in the front wheel. That we call it as 4x4. Okay, if you take that vehicle in the hilly area, okay, that you already get so much power from the one motor. So okay, if you use two motors in the one in the front wheel and the second one is the rear wheel, you will get better efficiency and better power to move forward your vehicle.
Okay, sir. Yes.
Yes. Anyone?
Sir, can we go for low degraded materials which is locally available? Means for we can say particular use of EV, for example 20 to 30 kilometer range, or as per the customer requirement. So here we can reduce the cost, or is any other kind of problems will arise?
Basically, if you use the cheap material, there may be some faults maybe can arise inside, because the power, the energy we are getting from the basically battery. Okay, then the motor controller is the main part that decides the position of the rotor. If you choose the lower quality of, or if you thought of there, because nowadays EVs, two-wheeler EV companies, they are using BLDC motors in the rear wheel. Okay, basically they fit the BLDC motor in the rear wheel. So they also say like they give a range of 40 to 50 kilometer in a single charge, but the main thing is how much power we are getting from the battery. Okay, so if you will sit two people in a two-wheeler, it might not give you a performance. Okay, so that time how you will think that that time you will think like BLDC motors they are using is not perfectly, and they might have chosen the wrong things to build the motor basically. Okay, so EVs, in the EVs we are considering the Ola and the Ather, and the hero is Veda. They are giving better performance. Okay, they are also using BLDC motor, but depends on the controller, how much how your controller is working. Okay, otherwise your motor won't get affected that way, that much. Okay.
Yes, sir.
Yes.
Thank you, sir.
Welcome. Anyone else? Anyone else want to say anything? This session is about 2 hours, but it is around 2.2 hours plus. So no issues. I hope you enjoyed a lot. And anyone have queries? Please ask me. You can follow ISI India on the LinkedIn. I hope everyone is following ISI India on the LinkedIn. And if you want to connect me as well, so you can direct connect with me on the LinkedIn. Okay, I am available there. My name is Akash Singh Chib. Okay, my name is, you can write it on the Google. The first name comes on your feed, Google. Okay, write my name as Akash. Akash Singh Chib, and please follow ISI India, Akash Singh Chib, and follow ISI India on Instagram and the LinkedIn. Okay. Thank you, everyone. We'll see you on the next session. I hope you enjoyed it. Thank you. Anyone have any queries? You can ask me. Okay. Okay, thank you.